what I want to do is talk about something really important right now in the space, and that's to do with voting. And I want to put a different spin, really, on voting. Now, currently, we're very familiar with the compound-style voting, and that's normally a delegation-based voting scheme. You have an ERC20 token, you delegate your voting power to some delegate, and you give that voting power essentially with unconditional strings attached, and on the hope that who you're delegating to is going to, when proposals come forward, they're going to vote in the way that you expect. So there is some level of trust in the delegate-based mechanism, and you have some issues associated with that, because once they have your vote, they can do certain things with that, or maybe they don't. So that's what this slide sort of is talking about here. We have some ghost delegates. So voting power is delegated to delegates that never use the voting power, and this concoction really comes together sometimes in some not so very fun ways. So recently, you may have heard about the Uniswap, Binance Smart Chain saga, and it all centered around their governance token and how they were going to govern the Uniswap protocol on Binance Smart Chain. And that obviously produced, a number of surprises. It's well documented, really. But what it ends up resulting in is voter apathy. So the delegation-based mechanism of compound-style voting is supposed to improve voter apathy. It's supposed to avoid the need for all of the voting power to be available all of the time to make important decisions. You delegate it to some individuals that are going to actively vote for you. But actually, stuff like this is starting to, create more apathy. And, really, voter apathy is basically a convenience issue. How much time and energy are you willing to put into voting? And how much is that going to cost you? Obviously, on Ethereum, that's going to cost you a certain amount to do the voting in that place. The problem as well with public blockchains have many advantages and benefits, but when it comes to voting, it is well known, well established that publicly knowing who votes, how they voted, or how they might vote is subject to coercion. And really, we have this notion that actually freedom of speech is freedom after you speak. The freedom to not be judged when you vote a certain way, and that's really an important nuance in this whole thing. So we have. So this is about giving agency of opinion back to a user. So what we want to do is actually take a different spin on this and think about how actually NPC-based systems can be used to alleviate this problem with private ballots. So this is the ability to vote, to have the credentials for voting, but not necessarily knowing how somebody votes. This is freedom after the speech. But also combining this with statement voting, which our cryptography lead is going to explain. So combining this with statement voting. So statement voting says, I will delegate my vote to an expert, and they can only use my vote in a certain way. So if I only care about somebody voting in favor of electric cars, I can say, well, I'm going to delegate my vote to this person, and if they try and vote for combustion engine-based cars, then my vote cannot be used. So they actually cannot go against your wishes and your desires, and that's really powerful, a voting-based system. So without further ado, I'm going to introduce our cryptography lead, Bing-Cheng Zhang. He's not able to make it to the event today, but he put together a really interesting, really informative video that will hopefully make you think a little bit differently about voting.
Hi everyone, this is Bing-Cheng from Zhejiang University. Today I will share our latest result on the coercion-resistant delegatable voting. It's designed for the blockchain on-chain decision-making systems. So when we talk about blockchain on-chain decision-making, two terms are quite popular in the community nowadays. One is called Treasury System, one is blockchain governance. Date back to 2018 when I was first proposing the Treasury System. The term was quite unfamiliar to the blockchain community. What is a treasury system? How it does to a blockchain? And at that time, I was still with Lancaster University, and I published a paper at NDSS 2019, discuss what is a treasury system, and discuss how to make a better use of collaborative intelligence of the blockchain stakeholders. In case you are still unfamiliar with this term, I will give a short introduction for the motivation. So when you talk about a blockchain itself is not a company. There is some organization or company behind it, right? And then we will ask who is going to fund the blockchain development or maintenance? And that's a treasury system. A treasury system basically collects money and redistributes money to some area and what we call projects. For example, you will distribute the money, you will pay the software development. Then you use the money to software development. You use the money for innovation, for the research. You use the money for marketing, maintenance, to rent servers, to make an advertisement, or etc., etc. Then how the money comes from? There are various sources. For example, the ICO. For example, what we call haircut or taxation. Each block reward, you may collect a certain percentage of them, and later, when you collect enough money, you redistribute them. Now the question is, who is going to decide where to use the money, where to spend the money? Then it comes my favorite quote from Abraham Lincoln: "The government of the people, by the people, for the people." So when you talk about a blockchain, you think about it's a government. Then who is going to make such a decision? And day back to 2018, I thought it's better to be all stakeholders. But the stakeholders have no expert knowledges. We need to involve experts in certain areas. For example, we definitely need to involve researchers to help us to make a decision on what type of research we need or how the company should go in the future. Here we need to talk about a term called liquid democracy. The term can trace back to 2002. That's the first time I know about liquid democracy. Brainford, on his homepage, posted a white paper called Delegative Democracy. Inside, it explains the mechanism about how to delegate your vote or how to vote directly, and later this mechanism is renamed to be liquid democracy. Underlying there is a source. If you are interested, you can have a look at it. But at that time, on this white paper, there was no implementation. And for years, there was no implementation. And there are certain difficulties to make it implementable to what we call conventional voting or what we call e-voting. So what is liquid democracy? I make a comparison. On the left-hand side, that's a conventional democracy, either direct democracy or representative democracy. If you are a short community, or if you are a small community, maybe you do direct democracy. Everybody directly vote on the issues. If you have an issue, you want to vote yes or no, then everybody will directly cast. And the representative democracy is for bigger countries, for example. And nobody can vote on the issue. You can only delegate your voting power to someone, and maybe they're expert, okay, to a short list of people. And this short list of people will vote on your behalf, and yes or no, something like that. So what is liquid democracy? Liquid democracy looks like a hybrid of these two versions. If you want to vote directly on the issue, you can vote directly on the issue. If you want to delegate to someone you trust, you can delegate to anyone you trust, okay? And the guy you delegated your voting power to can delegate even further. So there's no short list for you to choose from. You can delegate to whomever you want. For example, a grandma may delegate the voting power to his son or to her son to vote on her behalf, etc. So this is called liquid democracy. And how to realize liquid democracy? That's quite a interesting and hard problem. And we comes with a new concept, and the concept called statement voting. And by statement voting, I realized liquid democracy in certain sort of form. So what is a statement voting? When you talk about conventional paper currency or paper cash, it's just a paper, right? When you change it to electronic currency or cryptocurrency, you can add a lot of things to it. You can add logic to it. You can make it more interesting. You can make access control. You can make it carry different, you can even make it carry a program, for example, smart contract. Now, when you talk about paper voting or traditional voting and e-voting or electronic voting, currently the electronic voting, the main purpose is just to mimic the paper voting process, which I think did not explore the full potential of e-voting. Because when you turn a paper electron to an electronic one, you can add a lot of interesting things which couldn't have been done in paper voting era. And statement voting is a natural extension of conventional candidate voting. So when we go back to the conventional candidate voting, you start to vote, you usually have a ballot. And outside, in the ballot, you have the candidate names. And for example, you only select one of them, okay? You select Bob, and you kick Bob, and you put it into the voting box, and you go. So basically, you define your vote in your ballot, and you put it into the voting box, and you leave. That's your candidate, right? Okay. So what is a statement voting? A statement in computer science, it's a program. What we call a statement voting. Basically, instead of vote on an object or on a candidate, you put a program inside your ballot, and you express your opinion as a statement or program. Then you put the ballot into the voting box and you go. When we do the tally, we first execute the program, and then this program will determine your final choice, and that choice will be counted. For instance, we are going to have a conference, and then my friends maybe ask me if tomorrow morning I want to go jogging with the rest crowd. And my opinion is, if tomorrow is less than 10 degrees centigrade, I'm not going, it's too cold. If tomorrow is more than 10 degrees centigrade and it's not raining, I'm going, okay? And I casted my opinion, okay? If it's not raining, if it's above 10 degrees centigrade, I'm voting for yes. Otherwise, I vote for no. I cast my opinion as a statement, put it into the voting box, and I go, okay? Tomorrow, say it's raining, and I don't need to be there. People will open the voting box, will look at my statement, and find, oh, it's raining. Oh, his decision must be no, so we don't need to wait for him. So I can keep sleeping. So this is the power of statement voting. Basically, at a certain point, due to limited information, I couldn't make a decision at that point. But my opinion is still my opinion. So I write down my opinion as a statement and I cast a ballot. And it's a cool concept when you combine it with a blockchain. Because on the blockchain, there are many oracles. They feed you informations. And then your code could process on those informations and then will determine your final choice, your final candidates, okay? If we go back to the delegative voting or go back to the liquid democracy, how to realize it, you can simply say, I want to vote exactly as Alice votes. That's your statement, and that's like a copy her vote. That's like delegating your voting power to her. Or you can give a more complex statement. You can say if expert A vote for yes, expert B vote for yes, I vote for yes, otherwise I vote for no. That's another statement. You can implement lots of interesting statements in a statement voting. Of course, not all statements are valid because you might have a loop, delegation loop. You might have a hunting problem. For example, if the yes is winning, I will vote for no. If the no is winning, I vote for yes. Basically, use the partial tally result. And certain things are not allowed. This one is not allowed. So there's a short restricted range of statement you are allowed to vote for each statement voting system. For delegation, it only lets you delegate to somebody. Okay. So let's talk about the coercion-resistant voting. In the literature, there are only 3 types of coercion-resistant votings when we look at all the papers. One is called fake credential, one is called revolt, one is called trusted hardware. And here I did not compare trusted hardware. So trusted hardware, basically, it's more like, for example, you take a machine that help you to encrypt your ballots. You submit your ballot to the machine and the machine encrypt on your behalf, and then you post these encrypted ballots on the blockchain, and that's it. Because the coercer does not know, well, we need to assume some untappable channel, because the coercer does not know what candidate you submitted to the encryption machine, because this channel is hidden from the coercer. Then you can lie about your view. You can say, yes, I indeed submitted the candidate you wanted me to do so, and then this is the ciphertext the trusted hardware give me. This is a way to get a coercion resistant. Okay. For fake credential, it's mainly like I have a real credential, I have fake credential. Credential is something allow me to vote. If it's real, then my vote will be counted. If it's a fake, then my vote will not be counted. But nobody can tell the credential it's real or not just by look at it. At least the coercer could not tell. So that's called a fake credential. And the revolt is the most natural way for coercion resistant. It's like if somebody coerced you, ask you to vote on something you don't like, then you have choice to cast your vote again when the coercer left. So this has assumption. Basically, at the end of the voting, the coercer left you, then you still have a moment to cast a ballot. Okay. In practice, I like a fake credential more because it seems more practical, and you don't need to assume the coercer is with you at the end of the election or at the beginning of the election or in the middle of the election. You don't need to be worrying about that. You just need a free moment to cast your own ballot, and you give the fake credentials to the coercer, and that's it. So for the fake credential, let's look at the assumptions. The voters cannot be coerced at the registration phase. So what is the registration phase? Registration phase is the time you get credential, the time you give your ID to the authority, and the authority will give you something that allow you to vote electronically. For fake credential during the registration, the voter cannot be coerced because at that time you need to, in general, you need to register the real credential and the fake credential. So you shouldn't let the coercer know which one is the real, which one is the fake. But for revote, there's only one credential. You use this to vote. As far as you still know this credential, you can revote, right? So it doesn't matter if the coercer is with you. And for the need for store crypto state, what does it mean? It means if I am a voter, okay, I need to remember the real credential in certain way the coercer could not detect. For example, if the coercer took my laptop, I should be able to reconstruct or remember what was the real credential. And it need to be only known by me, shouldn't be known by the coercer. So this is some drawback of fake credential scheme or some limitations. The voter need to store some crypto state that is the credential, the real credential, unknown to the coercer. But for revote, it doesn't matter. You can tell everything to the coercer. Okay. Now, non-alienable mean of authentication, everybody needs. If you need the coercion, if you need a scheme to be coercion resistant, everybody, all schemes need to be the non-alienable or inalienable authentication. Basically, only you can be authenticated by yourself. Otherwise, if the coercer can take your ID card to authenticate on your behalf, then it's not what we think it's a meaningful coercion, because the coercer becomes you. It's like you did not exist, because they can capture you, lock you in the building, and he vote on your behalf. He go to the voting booth on your behalf. He go for authentication on your behalf. So we think it's a meaningless. So we think during the authentication, we still need the real voter to come to get authenticated. Then the coercer to be absent at some point, yes, or requires, because the trick of deceiving the coercer is to do something he did not know or he could not know. For example, we assume untappable channel. Untappable channel means it's a channel the coercer could not listen to, and even does not know it exists. For example, for revote, after the coercer left my room, I vote again, and that vote again behave shouldn't be noticed by the coercer. Otherwise, they will come back to my home and beat me. Okay. The coercer need to be absent at the end of the voting. That's the limitation for revote. Okay, as discussed before. Our scheme follows the fake credential paradigm. So now I first give a brief introduction on what is the fake credential paradigm. So basically, the black dot is a voter. I'm a voter. I go to the registration authority, short for RA, the registration authority. I give my ID card or whatever. I authenticate myself, and he would give me a credential. Okay. Well, along with this credential, he posted something on a bulletin board, what we call BB, about my credential. Well, may not directly tell what is my credential, because otherwise the coercer would know what is my credential. But he definitely put something on the blockchain that helps people to identify which credential is real, which credential is fake. Okay. Now the black dot, there's an adversary on top of it, means it's a coerced voter. Okay. If I'm coerced, I'm going to give a fake credential to the coercer. So that's sigma prime. the coercer will use the fake credential to publish or to submit a ballot. I will secretly use my real credential, Sigma, to submit a ballot. Well, at the end, the fake credential submitted ballot, the real credential submitted ballot will all be tallied together. But the fake credential submitted ballot will not be counted in an oblivious way, in such way that nobody can tell which ballot was counted, which ballot was not counted. But otherwise, the coercer will still realize, oh, this is fake, right? Okay. We proposed a new voting scheme, and we want to improve our old design. Our old design, by old design, I refer to our NDSS 2019 design, ZOB19, and that one was using algorithm, using a vector to represent your vote, and a vector of 0 or 1. If you want to delegate to some candidate, you mark the candidate to 1. If you want to vote directly, you mark the choice to 1. Yes, no, abstain, whatever choice to support the project, the choice. If you want to delegate to some expert, you mark the expert position to be 1. So it's a very long vector, and each element will be encrypted in an algorithm or lifted algorithm. So the communication is very big. It's what we call OM. M is roughly the size of the experts. The paper claims support liquid democracy. But because on the blockchain, you don't know each other. You can only delegate to the expert. So actually the functionality it does is you can either delegate to the experts or you can vote directly on the issue or on the project. But nobody knows you delegated or you voted. That's the mechanism called I call it delegative voting. Okay. The scheme is not coercion resistant at that time, and since now the smart contract become more and more popular, which means to buy a vote become more and more popular. You can simply write a smart contract to buy a vote. Anybody vote for yes, if you give me a proof, I give you how much money. And for some blockchain, it's even anonymous. You don't know who bought the vote. So it's a big deal. We want to make the scheme coercion resistant. And by that, we proposed, so far as we know, the simplest, the most efficient fake credential scheme. And then we reduced the communication of the ballot size. It was OM because it's a vector. Now it become O1. It's just a constant number of ciphertexts. And then we give better privacy because the old scheme reviews the voting power. And when we talk about democracy, we quantify your voting power by your stake, the amount of your linear to the amount of stake you have. So you have to lock the amount of stake to get the voting power. And note that it has to be freezed. It has to be deposited, locked during the entire voting period. Otherwise, you can first register your voting power, and then you transfer your stake to someone else, and someone else can use your stake to register again and again and again. No, that's unfair. So we need to let you lock down your stake, and with that amount of stake, we will proportional to map it to your voting power. Then you will start to use your voting power to make a decision, participate in the Treasury system. And at that time, the voting power was public, and this time we make it hidden, we make it private. Roughly speaking, the protocol looks like that. The voter will first go to the RA, Registration Authority, to authenticate himself and to get a real ballot. And the RA, well, it's an overview, okay, not exactly like this. I will give detail later. Then the RA will post the real PKs to the bulletin board. And I can create as many fake PKs as I want. I can post them to the bulletin board as well. And during the voting phase, if nobody coerces me, if I'm normal, I'm honest, I will use the real ballot to cast my the real credential to cast my real ballot. The credential is PK here. And if I'm coerced, then I will cast a fake ballot using the fake PK, public key. And during the tally phase, there are a number of ballots and the encrypted PKs. And then we will mix them using some mixnet and shuffle them and decrypt them and do it for tally. Roughly like that. I will give details now. So during the registration phase, what the voter need to do? The voter need to first pick a PK, and in the left hand side of the slide, it's called PKJ. I will first pick a PKJ. Basically, I know the SK, and this is the PK. It's a signing key. It's a public key for you to sign. And the bracket means you encrypt it. So you encrypted the PK. Well, if you think about it, Elgamal can encrypt it, okay? And alpha J is your voting power. You also encrypt your voting power. And TXJ is the transactions. Recall that I said you need to freeze or you need to lock your stake in order to register. And that transaction is the transaction for you to lock your stake. And then you give a proof. And the proof is a NISC proof, what we call tau J. So what it does? It proves the amount of stake you freezed in the transaction TXJ is larger than or equal to the voting power alpha J encrypted in the bracket alpha J. So bracket alpha J is a ciphertext, and the PKJ bracket is a ciphertext, okay? And you also prove inside the PKJ bracket is a public key, and you know the secret key about it, and you give a zero-knowledge proof to the I. The RA will re-encrypt your PK. That's very important. Re-encrypt your PKJ. Now, if you look at the right-hand side, it's lighter blue. Okay. Why re-encrypt it? Because then the coercer does not know what PK it is. Then you can lie about it. Because we break the view. We make sure the voter does not have the entire view of whatever the RA is going to post it on the blockchain. So now the coercer may come to ask the voter, what is the PK you created? The voter can give whatever PK he wants. Why? Because then when the coercer asks you, oh, by the way, you encrypt the PKJ, right? What's the randomness you use to encrypt it? He can say, well, this one, or that one. He can make an arbitrary one. Because it has been re-encrypted by the RA, then nobody can tell the link, okay? Obviously, the RA need to prove the correctness of the re-encryption, what we call designated verifier proof. So it only proves to the voter, and the voter can simulate the proof to the coercer. So later, when the coercer comes, the voter can simply give whatever PK, fake PK, and encrypt it, and match it to the re-encrypted ciphertext, and saying, well, this is a proof. This is a simulated proof. Okay, and the RA will also sign it to make sure this tuple is indeed produced by RA and posted to the BB. During the voting phase, or let's first talk about the ballot structure. You will cast a ballot, and the ballot is your PKJ created during the registration phase. VJ is your voting candidate. For instance, if you want to vote for the fifth expert, then you just put 5 here. If you want to delegate your voting power to the 9th expert, you put a 9 here. 145, you put 145 here. So it's just a single ciphertext, okay? And bracket means encrypted. And you give a sigma, you signs. This is your ciphertext using the secret key associated with PKJ. Since it's the only public key created by you, only you know the secret key, and only you can sign it. And you give a proof, pi j, a zero knowledge proof inside the ciphertext. It's a plain text, and you know the plain text, and you know the plain text is within certain range. It's a valid ballot. And everybody can check it, can check the signature, checks the NISC proof. If all verifies, then it's a valid ballot. If you are coerced, you give the coercer the fake public key, PKJ prime, fake one. The coercer can do whatever he wants. He can submit whatever VJ prime, encrypt it, sign it, make a proof, it's fine, whatever he wants. Okay, later I will show how to eliminate those ballots, remove those ballots. Okay, on the right hand side, it's the deceiving strategy. When the coercer comes to me, ask me for a credential, I give a fake credential, which is a PK prime J to him. And then I have to post something to the BB. What I post? I post encryption of PKJ prime. And I post encryption of 0, just encryption of 0. That 0 means the voting power associated with the PKJ prime is 0. And I give a delta, which is a sigma, which is a NISC proof, showing that I know the secret key of the public key of the PKJ prime. It's by me. Okay, I post it to the BB. All voters can post it to the BB. Everybody can post because it's a fake credential, if you can think about it. And recall that the real credential, at the below of the slide, I copied the real credential here to make a comparison. The real credential is submitted by the RA, re-encrypt your PKJ, encrypted PKJ, and it's encrypt of alpha J, which is your voting power, and above it's encrypt of 0, means your voting power is 0, and there are certain transactions, proofs, and signature of I. That's it. And those two, the first two items, we will truncate it and mix them together through a mixnet, so later nobody knows which one is real, which one is fake, and we will decrypt them and do something. Okay, then how to do it? During the tally phase, a ballot is like a PKJ encrypt of VJ, which is your actual ballot, your actual vote, and sigma J, your signature, and pi J, it's the NISC proof, as mentioned in previous slides. If both checks are valid, the signature and the NISC proof, you will take the first two items, okay, which is the PK and the encrypted vote. And you encrypt those PKs. By you, I mean the tally committee. Encrypt those PKs using 0 as randomness. So then you get a bracket PK1 to bracket PKN. Maybe I can use this. Okay, it's here. Okay, for better understanding. And then you have the encrypted votes here. Okay, now these are what's posted on the blockchain or on the BB by the RA, which is the real credential. On the right hand side, it's the fake credential, okay, posted by anybody else. Now you take the first two items here, and you take the first two items here, and you start to shuffle them together, shuffle re-encryption, put them together. Now you have a mix of the real credential, fake credential. I all call them alpha, but the sum of the alpha is 0, means your voting power is 0. If it's fake, the voting power is 0. And the left hand side, we mixed all the ballots using a mixnet shuffle, okay, to the purple one. So we re-encrypt them. So we have two things like that. Now let's talk about the tally procedure. After the matching, we have two columns. The first column is encrypted voting powers. The second column is the encrypted votes, basically the actually your choice. And we decrypt the second column, we get your choice in plain text because it's already mixed after the mixnet, so it does not reveal your privacy. We don't know who it's coming from, okay? And we don't know which alpha I is 0, which alpha I is something non-zero. As the same as before, we consider the expert as certain part of the candidate. For example, the first several candidates are experts, and the final few are the actual choice you want to make. For instance, if it's a project, you want to vote for yes or no, then you can think about S4 is yes, S5 is no. And the first several are the experts. If you want to delegate to an expert, you just vote to the expert. For example, number 3. If you want to vote on the issue directly, for instance, you want to vote for yes, you can vote number 4. Let's assume number 4 means yes, number 5 means no. Then you directly vote. With that, nobody knows you either voted or you delegated. Okay. For instance, if the first ballot want to delegate to candidate number 3, which is expert number 3, then we will take the encrypted voting power to here. Oh, by the way, the encryption is lifted algorithm for in our implementation. Basically, it's additively homomorphic. And if more than one people delegate to the same guy, for example, S2, there are alpha 5 delegate to him, alpha 7 delegate to him, we just multiply the ciphertext. By homomorphic property, you get alpha 5 add alpha 7. Basically, you sum the voting power together. So after this, we have the expert's choice. Expert choice, we can also decrypt them, and for instance, the voting power for S1 is alpha 2, and if he choose to yes, we will add alpha 2 to yes. If the voting power of S2 is alpha 5 plus alpha 7, and if he voted for no, then we will add this encrypted one. By the way, it's encrypted, nobody knows. Then we add the encrypted voting power to S5. After that, we counted homomorphically everybody's vote. For the voters' vote, if you vote directly, it's already at S4, S5. If we delegate to the expert, then according to the expert choice, we will vote. Basically, we will take their voting power ciphertext and add it to the final tally. So at the end, we get the yes-no final tally, encrypted U4 and U5, and we decrypt that. Then we get the, for instance, this 2 or 3. And then we get the final tally result. Okay, let's talk about the assumptions. For ballot privacy, the registration authority is untrusted because we have the mixnet. The shuffle committee, which is a mixnet, it's untrusted. Well, it's basically the shuffle committee does not know the secret key. So even if they collude together, they don't know what is it. And the trustee means the tally committee, the key holders. The tally committee will have a T out of an trustness, which means they form a threshold decryption, threshold cryptography. For verifiability, the registration authority, it's untrusted, the shuffle committee is untrusted, the trustee is untrusted, which means we have unconditional for verifiability. What is what we need? Verifiability is the most important thing. And for the coercion resistant, we have to trust the RA. Why? Because the RA re-encrypts your PK. If he collude with the coercer would know which PK is real, which PK is not real. And for the shuffle committee, we need to trust at least one member because it's a mixed net. Everybody shuffle, re-encrypt, give it to the next guy, shuffle, re-encrypt, give it to the next guy. And we need to make sure at least one of them is honest to hide the overall permutation. And for the tally trustees, tally committee, we still need to be T out of N. Otherwise, he can decrypt all the ballots. If he can decrypt all the ballots, then there will be a problem. Basically, the coercer would know how I voted. It seems that trust the RA is inevitable to any coercion-resistant voting schemes. Okay. Now, final comparison. We compare our scheme with the state-of-the-art coercion-resistant voting schemes. For example, the famous JCJ and the recent latest one is called Vote Again. We put our old NDSS paper called ZOB19 here, but that one is not coercion-resistant. Mainly, we want to show the improvement on the efficiency and on the voting power, etc. Okay. Now the first column is the voting power. The rest of the scheme is not designed for the blockchain voting, so their voting power is not differential. It's just one. Everybody, one guy, one vote. But on blockchain, we want the voting power to at least have a certain relation with your stake, with the amount of stake, right? We don't want the guy who has 1 Bitcoin have the same decision power as the guy who has 1 million Bitcoins to decide the fate of Bitcoin. So for the blockchain voting, we want the differential voting powers, and the REST scheme does not have. For delegation, the REST scheme only for coercion resistant. They did not take into account about the liquid democracy, delegative democracy, and this is a scheme. The first scheme, what we know, first does the coercion resistant as well as the delegative voting. And for ballot size, we reduce the old scheme to 01. Basically, it's several ciphertexts. Then for the tally complexity, because the old one uses homomorphic tally on each vector, so it's m times n. And in practice, later we find out m could be very, very large. The number of experts could be very large. So then we reduce it to the ON, which is the number of voters, which is the best you can do, most scalable voting system. For the crypto state, if you are revote, then the voter does not need to remember the crypto state. If you use a fake credential, then you need to use some mechanism to keep the real credential, which is a fake, which is a crypto state. For ballot privacy, everybody is using threshold decryption, so it's T out of N. For verifiability, except the voter again need to trust RA, everybody else trust no one. For the coercion resistant, we need to trust RA, and most of them need to trust RA. The voter again need to trust RA as well as the tally servers. Basically, it's a tally committee. With that, I would like to give some takeaways. First, we proposed a new scheme about the coercion-resistant voting for blockchain decision-making. And it's scalable compared to our old scheme. It's very scalable. The ballot size is constant, and the tally complexity is linear to the number of voters. It doesn't matter about the candidates, about the choice, about the experts. It's irrelevant, only linear to the number of voters. The scheme supports liquid democracy or delegative voting in certain circumstances. Basically, you can either delegate to some expert or you can vote directly on the issue. And nobody knows what did you choose. We designed a two-stage tally procedure to hide the voting power the voting power and the delegation power. The old scheme, if you recall, I'm not sure if any of you knows the old NDSS scheme. We need to review the voting power and review the delegations. If I'm an expert number one, we need to review how many voting powers people delegate to me. The tally procedure is highly efficient, only use shuffle and decryption operations. And in particular, it does not use so-called PET, P-E-T, which is a plain text equivalence test. In most schemes, to filter out the fake credential, they use a plain text equivalence test, which is a complex it's a very slow procedure. Very below, it shows how the scheme linked together with the blockchain. Basically, it has 3 epochs. One is the pre-voting epoch, another is voting epoch, and a post-voting epoch. Pre-voting epoch, people post some projects on the blockchain, and expert voters, they come to register. And for the voting epoch, we have the committee to host the voting and generate the election keys, and everybody cast the ballot. And in the post-voting epoch, and people do the tally process and sign the decision making, and everybody execute the decision. For example, transfer certain amount of money to certain projects account in terms of a treasury system. Okay. With that, I would like to conclude my talk. Thank you very much. If you have any questions, you can email me at bingshen@vju.edu.cn. Thank you. Bye.
Well, I'd just like to say thank you to Bingsheng for delivering that really technical, really insightful talk on statement voting, fake credential schemes, and trying to envision what the next steps might be for voting in the ecosystem. It's a critical part of the puzzle to allow the ecosystem to scale properly. Is getting the voting mechanisms correct. We are still, at the beginning of the beginning, and hopefully maybe a DKG-based a statement voting scheme might be something that is tried and tested.